questions after the warm-up. And if you finish the warm-up and you're good to go, feel free to just leave and have the rest of this particular hour off. For right now, just to get ready for the quiz tomorrow, and so that we can take a look at what solving these problems look like when not all of our entries are regular old values, but some of them are undefined variables. Today I have a warm-up that has that feature. It won't be the whole test tomorrow, but I will have some questions in there where some of the matrix elements are undefined variables. That means that your answer has to be in terms of such undefined variables. It just makes it so that I can guarantee that you are doing the question by hand and not just copying a thing from the internet. Item 1. And also the other thing about today's warm-up that I want y'all to notice is that at the top, I'm just going to define some matrices and then reuse them for all of these questions. That will be another feature that you see in tomorrow's chapter test. Item 1, take A inverse by shortcut and then show that A times A inverse gives back the identity matrix, where matrix A is A, 2, -1, and 3. And then on the right-hand side, I'm sorry, and then item number 2, give me the product of A, B, where this is A and this is B. And then finally, item 3, give me the determinant of the product CB by the shortcut. So once you take the product of matrices CB, how big will that matrix be?
3 by 3.
Yeah, it's going to be a 3 by 3. Matrix C is a 3 by 2. Matrix B is a 2 by 3. Those middle indices of the 2 and the 2 will cancel, and you'll get a 3 by 3. So first, do the product CB, and then take the determinant of CB by the 3 by 3 determinant shortcut. This is also a question I like because it's a compound request. One part, it's asking us to take a product. Second part, it's asking us to then take the determinant of that product. Of course, the answer here will be some sort of algebraic statement involving C, because again, one of the entries in this matrix is undefined. After that, I'll take questions on the review or general questions about the chapter or test. And like I said, if you don't need any of that, if you're good to go on these matrix manipulations, feel free to head out after the warm-up is over.
Hey, Mr. Robinson.
Yes?
I just said good morning.
Oh, okay. Good morning.
Yeah, good morning.
Okay, let's go ahead and start. So item number 1, we are being asked to take A inverse by shortcut, and then we're asked to show that the product of A and A inverse gives back the identity matrix. Of course, it should work both ways, both A inverse times A or A times A inverse. But in this case, I'm only going to ask for it one way, and that'll probably be the same on tomorrow's test, just because doing it both ways, you know, it's time consuming. Do look for the instruction though. It could be either way. I could give you A times A inverse or A inverse times A, or both, depending on what questions I decide to cut from the test. Nonetheless, A inverse by shortcut, what is that? What is that going to be? How do we take the inverse of a 2 by 2 by shortcut?
First, you find the determinant.
Yep, because it's going to be 1 divided by the determinant. And what is the determinant of this matrix?
A times D minus B times C.
Right, so what is that for this matrix?
Oh, 3A plus 2.
Okay, so this will be divided by 3A plus 2. Thank you. And then on the inside, we need to make the movements that we need to make so that this thing is the inverse by shortcut. So on this first diagonal, what do?
You switch the places.
Switch
we're going to swap those, so that'll be 3A. And then here, these are going to remain in place, except both of them are going to get hit by a negative.
Negative, yeah.
So this will be -2, and this will be +1. So that right there is a inverse by shortcut. Are there any questions on that first part? No? Okay. And now we need to show that A times A inverse will give us back the unit matrix. And so we're going to do A by A inverse, which is going to be equal to A, 2, -1, 3. And then we're going to multiply this by A inverse, which is 1 divided by 3A plus 2 times 3, -2, 1A. Now, it's important to keep in mind that while matrix multiplication is not commutative, scalar multiplication is. So that is to say that since this is just a number, right, this is just a scalar, I can take this and I can move it out to the front, and then I can conduct my matrix multiplication. Moving this around will not change the product, but swapping the position of the matrices might change the product. So this will be 1 divided by 3A plus 2, then times A2 -1, 3, which we are going to multiply by 3, -2, 1A. And when we do matrix multiplication, it's going to be row by column. So I'm going to take these rows and hit them against these columns. And so our product is going to be 1 divided by 3A plus 2, multiplied by the quantity of A times 3, which is 3A, plus 2 times 1, which is plus 2. And then our next entry is going to be A times -2, -2A, plus 2 times A, plus 2 times A. And then here in the bottom left, this is going to be -1 times 3, -3, 3 times 1, plus 3. And then for our bottom right entry, it's going to be -1 times 2, which is 2, plus 3 times A, plus 3A. Notice this is going to be 1 over 3A plus 2 times 3A plus 2. This is 0. This is 0. And down here, this is 3A plus 2. Anything divided by itself is 1, so this is necessarily 1, 0, 0, 1. Any questions there on item number 1? Basic homework question, find an inverse of a 2 by 2 by shortcut, and then verify that it is the inverse by multiplication. This works whether or not all of the terms are numbers. Any question on that first one? No? Okay. For the second one, just regular old multiplication. So we're being asked to multiply AB, and then I'll do question 3 on a separate sheet just because we will run out of space there. So this is just asking us to take A to -1, 3 and multiply it by 4, 0, 0, negative 1, 2, 3. And again, it's row by column, so we're going to take these rows. We're going to hit them against these columns. And what are the indices in my first matrix? How big is it?
It's a 2 by 2.
This is a 2 by 2, and this guy over here is a
2 by 3.
And so multiplication is possible because these inside digits align, and so our product is going to be a 2 by 3 as well. It should be the same dimension as this matrix. And so we're just going to go through, same as before. The only difference is it's going to produce 6 entries instead of 2. So our product of AB is going to be equal to 4A plus 0. 0 times A is 0, and then 1 times negative 2 is, well, negative 2. And then our top right entry is going to be 2 times A plus 2 times 3, which is going to be 2A plus 6. Down here in the bottom left, this is going to be negative 1 times 4 plus 3 times 0, so that's going to be negative 4. 0 times negative 1, negative 1 times 3, so only the negative 3 survives. And then for the bottom right entry here, it's going to be negative 1 times 2 for negative 2, plus 3 times 3 for 7. And so this thing simplifies down, and the only entry that we can actually simplify is this one. So it's going to be 4A, negative 2, 2A plus 6, negative 4, negative 3, and 5.
Mr. Robinson, is that last value correct? Because 3 times 3, it should be 9.
Oh, 9. Yeah,
Yeah.
I was jumping ahead, so that this is 7.
The answer is.
Yep, good. Okay, so this is the product. And then finally, the long one, the determinant of a 3 by 3. Are there any questions on these first two before I turn the page? No? Okay. So what we're being asked to do in item number 3 here is a compound request. We're being asked to first take the product of CB, which will give us a 3 by 3 matrix, and then we are asked to take the determinant of that new 3 by 3 matrix. So I'm going to say, well, I want the determinant of CB. And so the first thing that I'm going to do is I'm going to take the product of CB. So CB is going to be equal to 2, 3, 1, 0, 0, C. And then I'm going to take that and I'm going to multiply it by B, which is going to be 4, 0, 2, 0, negative 1, 3. Where this guy here is a 3 by 2. This guy here is a 2 by 3. The 2's align, and so we know that we can multiply them, and we also know that our result is going to be 3 by 3. It's going to be rows by columns. And so the product of our two matrices is going to be equal to, do it this way, 2 by 4, which is 8, plus 3 times 0, which is 0, so that one's just 8. 2 by 0, which is 0, 3 times negative 1, which is negative 3. 2 by 2, which is 4, 3 by 3, which is 9. So that's going to be 4 plus 9, which is 13. Next row, 1 by 4 plus 0, so that's just 4. 1 times 0, 0 times 1, so that one's 0. 1 times 2 for 2, 3 times 0, which is 0, so this entry is 2. Final row, so this is going to be 0 times 4, which is 0. Plus, 0 times 4, which is 0, plus 0 times C, which is still 0. 0 times 0, which is 0. C times negative 1, which is negative C. And then for our bottom right entry here, this is going to be 0 times 2 for 0, plus 3 times C for 3C. Is that okay for the product of CB?
Yep.
Okay. So then for our shortcut determinant, we're going to say that the determinant of this matrix, and technically the thing that I'm about to write, the act of writing the shortcut out like this, it's not math that you're writing out. The math that you're writing out is still the set of cofactors and minors. It's just that, you know, it's a way of organizing the math to quickly get the exact same answer. Like, what I'm doing here is not technically a math operation that can be named. It just works. So our shortcut here is going to be 8, 4, 0, -3, 0, -c, 13, 2, 3c. And for this to work out, I have to copy paste over the first 2 rows. So I'm going to take these columns. I'm going to take these 2 columns. I'm going to rewrite them over here. So this is 8, 4, 0, -3, 0, -c. And one way that we can produce the determinant of a 3 by 3 is by taking 3 of our positive diagonals, multiplying and adding. So I'm going to take this product, and this product. I'm going to multiply each one of those diagonals together, and I'm going to add those up. And then from that, I'm going to subtract this diagonal, and this diagonal. It gives us the same thing as our procedure of cofactors and minors, just maybe a little bit quicker. And so the determinant of the product CB is going to be equal to this first diagonal, which has a 0 in it, and 0 times anything is 0. So that first one is 0. Second one, also 0, right? If there's 1 0 in the diagonal, the whole thing zeroes out. And then 13 times 4 times -c, so that's going to be 40 plus 12 for 52.
Mm-hmm.
Yeah?
Yeah, -52c.
-52c. So that's our blue set. From that, we have to now subtract our yellow set. So it's going to be minus the sum of 0, 0, 13, that's 0. -c, 2, 8, so that's -16c. And then 3c for -3, so these two will give us -12. And then 12 times 3 will give us -36.
No, -48. Oh, no, sorry. Yeah. My bad.
3 times 12 is 36.
Okay. Yeah. So now we'll do these two, right? So it's going to be 16 and 36 for 52. So this is going to be equal to -52c minus -52c or
Plus
0.
52c. So it just becomes 0.
0. So what does that tell us about the character of the matrix CB?
There's no inverse.
There is no inverse, and there's also
No
No
solution.
solution.
no solution. Yeah. How about that? I like that set of questions. That's actually a pretty good representation of what you'll be looking at tomorrow. Though, like I said, only about half of the questions, maybe a little bit more, will have these unsolved values in them. The rest of them will be basically the same as the homework. And I mean, what I'm asking you to do here is the same as the homework. The only difference is you can't easily verify it by using your calculator. Are there any questions first on today's warm-up?
Mr. Robinson, on the test, will you specify whether to use the shortcut or long method for finding the determinant?
I'll take questions on the test momentarily. Are there any questions on today's warm-up? No? Okay. So to answer that question about the test, yeah, I'm going to specify what method I want everywhere. So you should be able to do the long and short version of all of the techniques that have multiple approaches. So in terms of shortcuts, here are the shortcuts that we have. There's a shortcut for taking the inverse of a 2 by 2. There's a shortcut for taking the determinant of a 3 by 3. I think those are the only two shortcuts that I taught y'all guys this chapter. Everything else, there's really only one way to approach it.
Mr. Robinson,
Mm-hmm.
the method we use right now, that was a shortcut, right?
That was the shortcut for a 3 by 3. The long way to do it is to use cofactors and minors.
Yeah.
Yeah. Are there any questions from recent homework or review?
So I was going to ask, if when you're doing Kramer's rule and the determinant is 0, is it also undefined?
Yeah, because Kramer's rule is actually solving the system. So if the determinant is 0, then the
Has no solution.
matrix has no solution. So that's why in Kramer's rule, if the determinant was 0, you can't divide by 0, and that's another way that you can show that it's going to be no solution.
Okay, thank you.
Mm-hmm.
Mr. Robinson,
Mm-hmm.
for Kramer's rule 2 by 2, once you have x, can you just plug it in another equation and get y, or vice versa, or do you have to do it both ways? Like,
It will technically, I mean, it will give you the correct answer, because if you get the correct answer for x and you resubstitute it in, then you get the correct answer for y, but that's not Kramer's rule.
oh, okay.
The act of doing Kramer's rule is the act of taking all of those determinants, yeah. And I mean, for a 2 by 2, taking the determinant is like trivial.
Yeah.
Because it's a test and you're taking it from home, of course, I expect you to show the work for the determinant. So I expect you to multiply this by this and then subtract this by this. But at this point in my life, I write the determinant of a 2 by 2 without showing any work, you know? That's like the one operation from here that is that straightforward that you'll be expected to just write it by inspection in the future.
Mr. Robinson, for Kramer's rule, even if we do get a 0 for one of the determinants, doesn't that just make that coordinate 0?
No, so if the, okay, it's a good question. So let's say that I have some overall, Kramer's rule says that the determinant when I swap out the x row divided by the overall determinant is that, and y is going to be equal to the determinant where I swap out the y row divided by the overall determinant. If this determinant is 0, if the determinant of the untouched matrix is 0, then it has no solution. If this determinant is 0, then that just means that x is 0.
Okay, I see what you mean.
Yeah, but the overall determinant, the determinant of the original augmented matrix, that can't be 0. If it's 0, there's no
Okay.
solution.
Perfect, thank you.
Mr. Robinson,
Yes?
can you take the determinant of a matrix that's not a perfect square?
Oh, that's a good question, and I apologize if I didn't mention that. No, only square matrices have determinants.
Oh, okay.
Yeah, the determinant is not really definable for any other object. And I guess there's one other interesting property I neglected to mention, but it really doesn't matter. What I'm about to say is irrelevant, but some of y'all might find it interesting. Y'all know how the identity matrix can be in any size. Like technically all of the following are identity matrices of different dimension. So I1 is just the number 1. I2 is 1, 0, 0, 1. We have a 3D identity matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. All of that good stuff. Technically, and I mean, you can prove this by hand, the determinant of all of these identity matrices, no matter how big it is, so the determinant of this, that, a determinant of an identity matrix of infinite dimension, infinite rows, infinite columns, no matter what, it's just 1. That's probably another interesting identity you guys will find useful in a few years. Not now, not this test, but I still think that's interesting that no matter how big it is, the determinant of an identity matrix is always 1.
Mr. Robinson,
Mm-hmm.
if we're solving the like on the test, if we're solving the determinant of a 3x3 with cofactors and minors, are you gonna tell us which row to use, or is that up to us?
I will probably not. Yeah, I won't tell you which row to use. So what's the smart way to do it? If you get to pick the row or column?
Zeros.
Yeah, whichever row or column has the most zeros.
Mhm.
Yeah. And I'm just going to say it out loud now because, you should be ready for it either way. I am going to ask you to take the determinant of a 4x4 using the system of cofactors and minors, because there was one of those in the homework. And because it's the same procedure, you're just going to go across and count the values off the rows and then produce cofactors minors. To do a 4x4 would be a nightmare, but I guarantee one of the rows or columns will have a lot of zeros in it, so that it's basically just taking the determinant of a 3x3, but with one additional step.
Okay. Because for 4x4, you have to reduce it to 3x3s and then 2x2s, right?
Yeah, you have to reduce it to 3x3s, then 2x2s. So if it was ugly and there were no zeros in it, then you would have to find the determinant of 4 3x3s. But if one of the rows is 0, 0, 0 number, right, then all of these 3x3s go away, and you only have one 3x3 left that you have to take the determinant of.
Okay, thank you.
Yeah, actually, let me see. I don't want to write out 16 entries in a matrix by hand, but let me see if I can find an example. It's a really common question that people think is clever. Because if you just take the first row or the first column or whatever, you'll be working on the problem for quite a while and you'll still get the same answer. But if you choose the row or column that's all zeros, then you'll have a good time. It'll be way quicker. I guess this kind of gives you some idea of what I'm talking about. It's one entry away from what I was thinking about. But yeah, so for this matrix here, if you went down the fourth column, you would have to find the determinants of 4 3x3s, right? Because each one of the minor matrices left behind is a 3x3. But if you choose row 3, 0, you don't have to worry about that 3x3. 0, you don't have to worry about that 3x3. And then you're only dealing with 1 times the determinant of a 3x3 and 3 times the determinant of a 3x3. Half the work, same answer. If you have any questions on the work, just holler. I'm going to assume everybody's just working or actually just going through their morning routine after they signed on their laptop. Breakfast, face washing, toothbrushing. Which I totally won't hate on. I'll be real with you. I have a class every night at 4:30 to 5:45. And sometimes I toss on the Bluetooth earbuds and I make dinner during the lecture. I'll still participate or whatever because I have the mic muted so that they can't hear me chopping or whatever. Just hit space bar and participate. But I don't need to take notes for that class, man. It's fine. Multitasking.
Mr. Robinson, what would you do for questions like number 17, where there's an exponents I think to the power of -1? Is that what it is?
It's an inverse.
It's an inverse.
Oh, right. So you have to find the inverse. Okay.
Yeah. Yeah. And actually, yeah, I don't want to yeah, so to that -1 in question 17, that just means an inverse. But actually, okay, just so we all know, just so that nobody freaks out or whatever, the thing that I'm about to write, obviously not on the test, it's just kind of interesting. Exponentiation is actually defined for matrices, which I think is wild. So if I were to ask you for A, B, C, D, E, F squared, right? What do you think that product is? What is something squared actually asking us to do?
Multiply the same thing to itself.
Yeah, so x squared is really just talking about x times x. So that is to say, take this object and square it with itself. So this would be equal to A, B, C, D, E, F multiplied by A, B, C, D, E, F. Anyway, how do we feel about that?
You can't multiply that.
Yeah, you can't do that. That's because this is a 2 by 3. This is also a 2 by 3. And these middle digits disagree with each other. So there is no product here. However, if you lost your mind, multiplication for any square matrices is well defined. So if I did this thing cubed, right? And this was 3, 1, 2, 0. Then it's literally asking you to take this thing and multiply it by itself 3 times in a row. So 3, 1, 2, 0, 3, 1, 2, 0, 3, 1, 2, 0. And normally matrix multiplication is not associative, so the order in which you would multiply this would give you back a different answer. But in the specific case of taking a matrix and multiplying it by itself several times, This is commutative, so multiplying these two together first, then this, will give you the same answer as multiplying these two together first, then that. But yeah, to the -1, that's just an inverse. All right. Hey, y'all, give me 1 second. I'll be right back. Though, of course, like I said, if you're like cool off this stuff, feel free to head out. 3 of y'all already did. Give me 1 second. I'll be back in case you guys have any more questions. Oh, yep, like half the people bailed. Huh. If y'all are still in here, I assume you guys are working. So like I said, if y'all have any questions, just holler. Probably shut the stream down in about 10 minutes. So try to get those questions in if you have them.
Mr. Robinson,
Yes.
how would you do questions like 20?
Oh, okay. Yeah. So if you have the determinant of a matrix, and I put this in the notes, but it was pretty small. There are a few properties that we can be aware of, and I wrote the test. There's not a question like this on there, but it's still good to know. If the determinant of matrix A is equal to -6, then here are the transformations that will be caused by those movements. Sorry, give me 1 second. I just want to check one sign. Oh, okay. So 20. What would the determinant be if you switched rows 1 and 3? So swapping 2 rows in a matrix is going to change the sign of the determinant, but not the magnitude. So row swap will just give us a determinant of +6. If you multiply a row by a constant, that constant is going to get multiplied into the entire determinant. So you multiply by 12, that'll give us 6 by 12, which is going to be equal to 72. And then if you take the inverse of a matrix, if you take the inverse of a matrix and then take its determinant, it's going to reciprocate that determinant. So then the final answer is going to be 1/72. So first one is a row swap. That changes the sign. And that's as many row swaps as you want. So if you row swap one set of rows and then row swap another set of rows, then it'll give you back the original sign, because every row swap gives us a -1. Multiplying a row by a constant just multiplies that constant into the determinant, which I actually think is pretty clear if you think about the shortcut for 3 by 3. Because if you multiply one row and you make it bigger by some constant, then when you take those diagonals and multiply them together and these diagonals and multiply them together, then they would all get bigger by exactly 1 factor of 12. So it's going to make your final answer bigger by exactly 1 factor of 12. And then, yeah, for the determinant, it's 1 over the original determinant for inverses.
All right, thank you.
Mm-hmm.
Gaussian elimination is really annoying, man. Like if you get if you do one mistake, your whole answer is wrong.
Yes.
There's a bunch of work to do, so you have to be really careful.
Yeah, it's crucial that you are very careful when doing Gaussian elimination. I would also remind you that, like, that thing in high school where the question becomes fractions, and then that's an indicator that you did something wrong, because usually high school textbooks are designed to protect you from that. You know, when you're dealing with matrices for a real life problem, like if it's relevant to your work as an engineer, they're all going to be fractions or decimals or something obnoxious to deal with. So that ability to know step by step whether or not you're doing it right, it goes away very soon. Okay. Okay. Good luck getting ready for your test tomorrow. I'll see y'all bright and early. You'll have just one class period to do it and get it uploaded. Take it easy, and I'll see y'all tomorrow.
Sure.
Bye-bye.